Okay, so when we look at these compound angle identities, it's important for us to know, just like when we were working with logarithms, the cos of x plus y is actually not equal to cosine actually distributed into that bracket. So just like we can't distribute a logarithm into a bracket, I can't distribute cosine or sine or tan or really any trig identity into its own bracket, right? This is the cos of x plus y. It's not the cos times x plus y. So that leads us to the question, what is this actually equal to? What is, if the cos of x plus y isn't equal to cos x plus cos y, what is it equal to? No, it's not. It doesn't work the same as log rules either. So I'm going to use this, this little triangle to kind of help us prove this in two different ways. So I'm going to show that the cos, one of these sides of the triangle is cos of x plus y, and then I'm going to show with the other side of that triangle what that is equal to. So we need to just start by filling in some information into this triangle. So I'm going to look at this triangle first, this guy down here. Okay, I have a 90-degree angle, or pi over 2, and I have an angle x. What do I know about this angle?
That it's 90 plus x.
Close.
X plus 90.
90 minus.
It's 90 minus x, or in other words, pi over 2 minus x, because we're working with radians, right? So I'm going to label this pi over 2 minus x. We know that all angles in a triangle must add to 180 degrees, or in other words, pi. So if this is 90, or pi over 2, these two must add to pi over 2. Okay, so that leads us to this right angle triangle here. So if this is y, and this is a right angle triangle, what do we know about this angle now? It's also pi over 2 minus y. Okay. Now what do I know about these three angles right here?
If you add them all together, you become 180.
Yeah, they are on a straight line. So they must add to 180, or in radians, they add to pi. Okay, so if I know that one of these is 90, and one of these is pi over 2 minus x, what's the remaining angle? What's this guy? Which would end up being? These three angles really add to these three angles, don't they? If one of them is pi over 2 minus x and one of them is the right angle, the last one must be this, right? Must be x. Or in other words, if I do pi minus pi over 2 minus pi over 2 minus x, all that I'm left with is x. So this must be angle x. Okay, what does that make this guy? This triangle is very similar to this one that we have here, right? This one is also pi over 2 minus x. Good. Okay, we're going to fill in the remaining angles here. So, what is this guy?
Pi minus pi over 2 minus x minus pi over 2 minus y.
Okay, so we know that all of these must add up to pi. So this must be pi minus pi over 2 minus y, also minus pi over 2 minus x. What does that result in? I think the pi minus pi over 2 minus pi over 2, those will cancel. And then I'm simply, so when we bring this in,
Pi minus x y. Pi minus, no. Pi plus x y.
so this is just 0, right? So what are we left with? We're left with x plus y. Okay, so here's x plus y. And what does that make our last angle?
Pi pi over 2 minus x.
Yes, yeah. In brackets, yes. So it's pi over 2 minus the other angle, which is x plus y. Cool. Okay. So now I want to deal with the sides of some of these triangles here. So what we kind of have to understand here is what I have written on the board for you over here, and I'll add it to our lesson as well. And that is, maybe I'll just add it above. If I have that cos theta equals adjacent over hypotenuse, if I wanted to find, let's say, the adjacent side, and I wanted to isolate that, I would multiply up the hypotenuse, and I would get that cos theta would be, or the adjacent is equal to the hypotenuse times the cos of the angle. Agreed? Okay. So if I wanted to find, let's say, in this bottom triangle that I see, based on x as my reference angle, if I wanted to find this adjacent side, what would my adjacent side be equal to here? Well, in order to do that, I first need to find the hypotenuse of this triangle, right? It's equal to the hypotenuse of cos times x. So maybe we can enter in that hypotenuse once we have it. Similarly, if I wanted to find the opposite side, let's say, so if this is my opposite side, I have written on the board for you over there that if we have sine of theta equals opposite over hypotenuse, then the opposite side of my triangle must be the hypotenuse times the sine of the angle that we're working with as our reference angle. So in this case, my opposite side would be whatever the hypotenuse is of this triangle, which is this side right here, times the sine of our reference angle, which in this case is x. Okay, so I still need to know what that hypotenuse is in order to figure out what those extra sides are. So we'll come back to that in a second. Jeremy? Okay, so can you tell me how you got that?
For the line triangle,
Yep.
hypotenuse is 1.
Yep.
So you multiply the cos y, this is adjacent, which is the hypotenuse of the x.
All right. So Jeremy is telling me, so using this similar formula here, but now I'm looking at this triangle inside here. The adjacent side to that triangle is 1, or in other words, the hypotenuse times the cos of the reference angle, which ends up being cos y. So this side we can consider to be cos y. So I can actually enter that into my side lengths for the red triangle now. Cos x, cos y, and this must be equal to cos y sine x. Okay, I'm going to also add in this side measurement right here. Can somebody tell me what that side measurement would be in relation to y as the reference angle? This opposite side, we said, must be equal to the hypotenuse times the sine of the reference angle. And the hypotenuse here is 1. So this side must be equal to the sine of y. Okay, so this side right here is sine y. Okay, so what I'm really interested in is what is this little measurement here? Let's use x as our reference angle inside here.
Sine y plus x.
Okay, so this side is the adjacent side of this triangle. So we said adjacent is equal to the hypotenuse of the triangle times the cos of the reference angle. And my hypotenuse we just found to be sine y. So this is sine y cos x. Okay, we're almost there now that we have this. I am additionally, I'm just going to erase this if I can. No, of course not. Okay, we'll do it off to the side here. I'm also interested in this side length right here. So let's just do that up here. What is that one equal to? That's the opposite side to our reference angle x. Jeremy?
Sine y, sine x.
Okay, so it's equal to the hypotenuse times the sine of the reference angle, and we said the hypotenuse is sine y. So this side length is sine y sine x. Okay, now we have two sides left to find. We have this side, right here. I want that side measurement, and I'm interested in this side measurement.
So the adjacent side would be cos x plus y.
Okay, so we're going to use the simpler one as our reference angle. So this one will be, and keep in mind the hypotenuse of this triangle is 1. So the adjacent side to this will be the hypotenuse, 1, times the cos of the reference angle. So it's just the cos of x plus y for this little side here. And how about this guy over here? The opposite side must be the hypotenuse times sine of the reference angle, which is sine of x plus y. So this is actually pretty cool because we've actually proven two trig identities just by filling in this information here in general. I know a couple things here. I know that the top length of this triangle, so I'm talking about this length, this entire length on the top of my triangle, must be equal to the bottom length. Or sorry, did I say triangle? Rectangle. Do you guys agree? Yeah, this is a rectangle. It has all right angles. That means opposite sides are equal and parallel. And so I also know that these guys must also be equal. So I was interested in proving what the cos of x plus y was equal to. Now, this orange side measurement right here, this guy, is cos of x plus y. Could somebody tell me an expression using the top of the rectangle and the bottom of the rectangle what the cos of x plus y is equal to here?
Cos x plus y equals cos y plus x.
Not true, actually, right? The cos of x plus y is only from here to here. I also have this little slice right here, which we said was sine y sine x. So how do I create an expression for cos of x plus y?
Cos x y plus sine y sine x equals cos y cos x.
Okay, so the top added together must be equal to the bottom, which we said was cos y cos x. Now what is cos x plus y? How do I get cos x plus y by itself?
You isolate, or
Yeah. So we're just going to bring the sine y sine x, or I'm going to write it as sine x sine y. Doesn't really matter the order. I'm going to bring it to the other side and we'll subtract it. So the cos of x plus y is actually equal to cos x cos y minus sine x sine y. Okay? Let's look at our identity sheet. Cos of x plus y, it's right here. We just figured that out, right? It's cos x cos y minus sine x sine y. Okay? The nice thing about this proof is we can also prove what the sine of x plus y is equal to. So that's using the sides of my triangle. So if I know that this side is equal to this side, can somebody create an expression for what sine of x plus y is equal to using the other side of the triangle? That's right. It's sine y cos x plus, so that's the first part of this right here, plus the second part, cos y sine x. I believe in your identity sheet it's like cos x, or it might actually be even in reverse. It might be sine x cos y plus cos x sine y, but same thing. It's all being multiplied and added. So that's actually this identity right here. So we just proved 2 of those. Am I going to make you reproduce this proof? No, I'm not. I just want you guys to see where these identities are coming from. And I wanted you to pay attention very closely. Okay, so now we know that these are true. I think we can prove the subtraction ones now with those addition ones. So we are going to prove a couple other compound angle formulas. So let's look at cos x minus cos y. What I'm interested in doing here is I'm going to use the addition formula, which is the cos of x plus y, in order to prove this. So I'm going to start with the left side over here, and we're going to eventually get to the right side. Okay, there's not much work that I'm going to do on the right side, so I'm just going to kind of copy out the right side here. And this side is the cos of x minus y. Okay, how could I use an addition in the cos of x minus y? How would I change this to the cos of x plus something? I still need the negative there, but how can I use an addition? Yeah, we know that a positive and a negative create a negative, right? Okay, so here's the thing that we need to understand. When I'm working with these identities, you need to consider your x's and y's just as somethings, okay? So don't write this down. I just want to kind of do a little kind of questioning thing here. So we just proved that the cos of x plus y is equal to cos x cos y minus sine x sine y, right? So we know this. Okay? What about cos of x plus 2? What's that equal to? Well, it's going to be equal to the cos of x times the cos of the second something, which is 2, minus the sine of x, times the sine of the second something, which is 2. Agreed? What if I do the cos of negative x plus y? What's that equal to? Well, it's going to be the cos of the first something, which is negative x, times the cos of the second something, minus the sine of the first something, which is negative x, times the sine of the second something, which is y. Okay? So these are just somethings. We're just saying as long as I plug in here, here, and here, the same thing, and same thing with this, the second something goes here and here. As long as those things match, this identity still holds true. So can somebody tell me what the cos of x plus negative y would be equal to? Good. Sine x. Sine of negative y. Awesome. Good job.
Oh, yes. So
Okay, so now we learned in our first lesson that we have even and odd identities. What is the cos of any negative something equal to? It's equal to the cos of the positive something. So the cos of negative y is equal to the cos of positive y. I'm getting that from the even and odd properties from our trig identities here. And what is the sine of any negative something equal to? Negative sine of the positive something. So I have a negative times a negative here. What's that going to give me?
Positive.
A positive. And now we've proven the cosine subtraction formula. So left side equals right side.
What happened to the negative y?
In this part.
Yeah, in both parts.
So I'm using the even and odd properties up here. These guys. So I know that cosine is an even function, so the cosine of a negative angle is actually equal to the cosine of its positive counterpart. So we're using the even identity here. And here I know that the sine of any negative something is equal to the sine or the negative sign of that positive something. So I'm using the odd identity here. Cool? All right. The tan addition formula. The tan addition formula. Let's take a look at this guy. So again, I'm not really going to do much with my right side here. Okay, so my right side's just going to remain kind of small. That's where I'm headed. But I do want to use some of my previously proven identities with my tan identity. So what do I know about tan? I already have an identity where tan is equal to something. What do we know?
Sine of X.
Okay, so tan is actually equal to the sine of whatever is inside the tan over the cos of whatever is inside the tan. So you guys agree that the tan of x plus y should be equal to the sine of x plus y over cos x plus y? Okay. Do we know how to expand these guys on the top and bottom here?
Well, according to here, yes.
No. What is sine x plus y equal to?
Sine y cos x plus cos y sine x.
Right. So we don't distribute the sine and the cosine inside, right? We use the addition and subtraction formulas. So I'm going to use the addition and subtraction formulas to expand. I'm actually going to write this guy just in a bit of a different order here, just because this is the way it's actually, how is it shown on our identity sheet? Yes, cos x plus. Okay, so I'm going to actually recopy it out like this. So I'm just switching the order of these two guys here. Hey, it's the same thing. It's like saying 7 plus 1 or 1 plus 7, right? I can write those however I want. So I'm going to expand this out. It's going to be the sine of x times the cos of y, okay, plus the cos of x times the sine of y, over, actually I'm going to leave myself a little bit of space in between here. Leave yourself some space underneath. And then cos of x plus y, we said was cos x, cos y, minus sine x, sine y. Move that over a little bit.
And that's sine x cos y with a tan.
It does not.
Not yet.
Not yet. Okay, so we have to actually, in this proof, this is actually a pretty cool proof, we have to actually look at where we're headed. So from this, on the left-hand side right now, I need to get to a tan x plus a tan y on top. I need a 1 in this location where we have cos x, cos y. And I need a tan x, tan y where I have sine x, sine y. Okay, so I just want to focus on that 1 right now. How do I make cos x, cos y equal to 1? What would I need to multiply it by? Not 0. It'd be 0 if I multiply it. Oh, okay. So if I take this, now I can't just do that to one term, right? I have to do that, if I'm going to multiply it, I have to do it to every term on bottom, and I also have to multiply to the top as well. But Jonathan is suggesting that the only way that I'm going to make cos x, cos y equal to 1 is if I multiply it by 1 over cos x, cos y. But I'm going to have to do that to both terms on the bottom, and I can't just multiply something into both terms on the bottom. I must also multiply that thing into the top as well. Okay, so I want you to think about all of these as if they're over 1 right now. And we're going to multiply in cos x, cos y. So let's see what we have now. So I'm basically putting every single term over cos x, cos y. Okay. Now, kind of a cool thing you'll notice is happening here. Yes, we have intentionally created this so that this bottom left guy is equal to 1. Anything divided by itself is equal to 1. So now we have 1 in that location. Now there's a couple other things that actually cancel out in some of our fractions. So let's just take a look at each individual fraction here. What cancels out in this first fraction? The cos x, the cos y's cancel. And what is sine x cos x? That's tan x, right? All right. How about the second fraction here? What cancels in the second fraction? The cos x's. And now I have sine y cos y. Alexandra? It is tan y. Okay, and then we said the bottom left one is just everything cancels, so it's equal to 1, which we have here. And then I've got two pieces right here. I've got a sine x over a cos x, and I've got a sine y over a cos y. What is that equal to? Tan x, tan y. And have we proven this now? Do we have left side equals right side? Yeah, we do. That one is a bit of a tough proof in order, like if you were doing it by yourself. But now you know the technique, right? So you can use something similar with the tan subtraction formula, or you can use even and odd functions for the tan subtraction formula.
Wait, what were the things that you bought?
I'm just showing that this is like tan x. Okay, and then our last proof here, proving the sine of x minus y. We're going to do something similar to what we did above. So I'm not really using the right side very much. It's just going to be what I'm headed toward. Well, we're going to use the expansion formulas that we just figured out in the above proof in this guy. So I'm probably going to just expand similarly here. Okay, you can always work your way backwards. Like you can do the opposite of what we did here and work your way up from here, right?
How do you know we're not supposed to do anything to the right?
Because I already have the expansion formula for addition, so I'm just going to use addition to expand out the subtraction. And also because I'm telling you. So now you know. Okay, so we're going to do something similar to what we did above, and that is we're going to use the addition formula, which we proved on the first page, in order to expand with the subtraction in for y. So if I know that the sine of x plus y is equal to sine x cos y plus cos x sine y, if I'm replacing the y with negative y, essentially I just have to plug in negative y for both of these y's here instead of the regular positive y. Okay? So the sine of x plus something is equal to sine of x. Now instead of cos y, we're plugging in cos of negative y, because that's what my second something is. Right? So it's cos of negative y this time. And then it's going to be plus the cos of x. X hasn't changed. But the sine of y now is going to be the sine of negative y, because we changed our y to a negative. So plus cos x, sine of negative y. Okay, this is almost exactly the same as the cosine proof, except we're just using the sine addition formula now. And I'm just going to use even and odd functions here now. So we have the cos of a negative something. What do we know about the cos of any negative something? It's equal to the cos of the positive something, so the cos of y. And what do we know about the sine of any negative something? Not positive. Cos is an odd function. So let's use our even and odd identities above. The sine of a negative something is equal to the negative sine of that something. So this one will be negative sine y. And then I'm just going to simplify the positive and the negative here. So what's a positive times a negative? It's a negative. And do we have left side equals right side? Yes, we do. Okay. We're going to put a little box there. Okay, so we've actually proven all the compound angle formulas except for the tan subtraction one. That's going to be your job to prove that one. But we've proven all the addition formulas and then the sine and the cosine subtraction formula. It's pretty good. We've learned a lot of new trig identities here. Okay, do you guys need a quick mental break after those? We'll take 2 minutes. Okay. Okay. So we're going to apply some of our compound angle identities. So what we want to just remind ourselves of are the special triangles here. So my goal would be to have a reference angle of pi over 4s, pi over 3s, or pi over 6s. And we know if our angles are past pi over 2, we can also use the cast rule to decide on negatives and positives if necessary. So something like the sine of pi over 12. Can you take out your headphone, please? Something like the sine of pi over 12, we wouldn't typically be able to find an exact value for this. But if I could split up pi over 12 either into an addition or a subtraction of two values that could potentially reduce to either pi over 4s, pi over 3s, or pi over 6s, I could actually use the special triangles. So, are there any ideas for how we could split up pi over 12 into maybe a subtraction of two things or an addition of two things that would reduce to pi over 6s, pi over 3s, or pi over 4s, or a combination of those things? Okay, one at a time. Claire?
Pi over 3.
It needs to be like an addition or a subtraction of two things.
2 pi over 6 minus pi over 6. No, wait, no, that makes sense.
Pi over 6 times pi over 2.
Sorry, 2 pi over
Not
12
times.
minus pi over 12.
Additions or subtractions? Jeremy? Okay, and how did you get that? So 1 pi over 12, I could do 4 pi over 12 minus 3 pi over 12. Agreed? And then when we reduce these, we get pi over 3 minus pi over 4, right? So it would follow to say that the sine of pi over 12 must be equal to the sine of pi over 3 minus pi over 4. Do we have a sine of something minus something formula that we could use to expand this now?
It would be sine pi over 3 cos pi over, cos negative pi over 4 plus.
Okay, so I'm going to use the subtraction formula rather than the addition formula. So if my first thing is pi over 3, it's going to be the sine of pi over 3, and the second thing, if that's pi over 4, is that what we have? Yeah. This will be pi over 4 and pi over 4 here, and I'll plug in pi over 3 for the x's. So if the sine of x minus y is equal to sine x cos y minus cos x sine y, it's going to be, in this case, the sine of x, or pi over 3, right? Like this is my x and this is my y in my formula, times the cos of pi over 4. And then if we look back at our identity here, minus the cos of the first thing times the sine of the second thing. So minus the cos of the first thing, which is pi over 3, times the sine of the second thing, which is pi over 4. Okay, so think of this as your x and your x and your y and your y in our expansion formula. Okay, so what is the sine of pi over 3? Let's use our triangle. Sine of pi over 3, if that's my reference angle, is equal to root 3 over 2. Oops. Okay, so we're just using the triangles now. Cos of pi over 4.
That would be 1 over root 2.
1 over root 2. Cos of pi over 3.
That would be, what's it called? 1 over 2.
1 over 2. Good. And the sine of pi over 4 is actually equal to the cos of pi over 4, which is 1 over root 2. Okay, before we go forward here, I just want to rationalize the denominator for 1 over root 2. So I'm just going to multiply the top and bottom by root 2 and root 2 on both sides, just so that I don't have to rationalize at the end. Becomes root 2 over 2. Okay, root 2 times root 2 is just like root 2 squared. So the root and the squared cancel out. Okay, and then I can just multiply the tops, multiply the bottoms. So root 3 times root 2 is root 6. 2 times 2 is 4. 1 times root 2 is root 2. And 2 times 2 is 4. And we can just actually put these into one fraction now. Questions on this one? Okay, negative 5 pi over 12. We need to create a combination of values that will reduce to things with reference angles of either pi over 6s, pi over 4s, or pi over 3s. What is a good combination? I'm probably going to have to do a subtraction here because this is a negative, right? So I'll have to have some negative value somewhere in there. So I could do like 2 pi over 12 minus 7 pi over 12, but 7 pi over 12 doesn't reduce to anything. I could do 1 pi over 12 minus 6 pi over 12, but again, 1 pi over 12 doesn't really reduce to anything.
5 over 12 minus 8 pi over 12?
Could that work? Let's try. 3 pi over 12 minus 8 pi over 12. When we reduce here, we get pi over 4 minus 2 pi over 3. Okay, that actually works, right? Because we have pi over 4s and pi over 3s. We should take note that this 2 pi over 3 is actually over here in the second quadrant, so it's in the sine quadrant. So if I do like the sine, cos, or tan of 2 pi over 3, only sine will be positive in that quadrant, but tan and cosine of that value will be negative in that quadrant. Okay, so the tan of a negative something, we said we can use, we proved the tan, well actually we didn't prove the tan subtraction formula, but we're going to use it anyways. It's the tan of x minus the tan of y over 1 plus tan x tan y. That's what I'm going to use here. So tan of pi over 4 minus 2 pi over 3. I'm going to think of this as my x and this as my y. Okay, so I'm going to get the, looking at our formula here, I'm going to get the tan of the first thing minus the tan of the second thing, which in our case here will be tan of pi over 4 minus the tan of 2 pi over 3. And we know that's over 1 plus the tan of the first thing times the tan of the second thing. So 1 plus the tan of the first thing times the tan of the second thing. Okay, tan of 2 pi over 3 is simply going to be equal to the negative tan of pi over 3, right? Because it's in the sine quadrant. So before you enter in your values, you could also just say here that this is equal to negative tan of pi over 3. So just using the cast rule there. And same thing with the bottom guy here, negative tan of pi over 3. Okay, so what is the tan of pi over 4 and what is the tan of pi over 3? Well, tan of pi over 4, if we look up here, is opposite over adjacent. So it's just going to be 1 over 1, which gives us 1. So I'm going to enter that in for both my tan of pi over 4s, 1 and 1. This is going to become plus here, minus a negative. And what's the tan of pi over 3? Here's pi over 3 here. Root 3 over 1, yeah. So it's just root 3. Okay, I would expect you guys, now that we're in grade 12, to answer all of these with rationalized denominators. Does anyone remember how to rationalize something with an addition or subtraction in the denominator like this? Jeremy?
Now I'm just going to say multiply it by the root 3 then.
Right. So we have to do something different for ones that have like multiple terms on the bottom. Okay, I'm going to multiply by what's in the denominator, but we're going to kind of create like a difference of squares here. So what it's going to end up being is I'm going to multiply the top and bottom by the same thing that I see on the bottom, which is like the 1 and the root 3, but I'll switch whatever sign is in between those two terms. So just on the board off to the side here, if I do 1 minus root 3 times 1 plus root 3 and I FOIL these things, I'm going to get 1 times 1, which is 1. 1 times positive root 3, which is positive root 3, 1 times negative root 3, which is negative root 3, and negative root 3 times positive root 3. What's negative root 3 times positive root 3? Or in other words, root 3 squared. Root 3 times root 3 is root 9, right? What's the square root of 9? 3, so it's negative 3. So what I end up with here is these actually cancel, and I get 1 minus 3 on the bottom. And that gives me negative 2. That's how we get rid of the root. So I can actually write this as 1 plus root 3 squared over 2. Or over negative 2, actually. And I would consider factored form to be simplest form here, so you can actually just leave it there. Okay, last couple here, and then you guys will have some time to work. This one is kind of like what we did above, but in reverse. So I have the cos of something times the cos of another thing plus the sine of that something plus, times the sine of another thing. Now if I look at my addition and subtraction formulas, I would like to find a pattern that fits within what I'm given. So what I'm given is I have a cos. Is it minus or plus? Plus a sine. Which addition or subtraction formula gives me a cos plus a sine? Look at all these here. Which one fits the pattern? First one, cos plus a sine. So this is going to go back into the cos of the first thing minus the second thing. Okay, in this case, my first thing is the first thing that I see on here. So that's like my x, and this is like my y. So this will be the cos of x minus y. That's what the formula says. And then I can actually just subtract these guys. So 7 pi over 12 minus 5 pi over 12 is 2 pi over 12. And when I reduce, I get the cos of pi over 6. Can we figure out the cos of pi over 6 without using our calculator? We have triangles that can help us with that, right? Let's look up at our triangles. What is the cos of pi over 6, if that's my reference angle?
That would be root 3 over 2.
Root 3 over 2. Perfect. Any questions for that one? Okay, so for our last one, it's asking us to evaluate the sine of A plus B. A and B are angles in the second quadrant. So we have, if I draw this out here, we have two triangles. We have one with angle A. And it tells us that both are in the sine quadrant. So I'm going to say that's my angle A1 and my angle B, where these guys are right angles. And I know that the sine of angle A is equal to 3 over 5. That's like my y over r, or in other words, it's opposite and hypotenuse. What I would need to know is x here. Okay, and then for B, I know that opposite is 5 and hypotenuse is 13, or in other words, y and r. I know 5 and I know 13. And I need to figure out x. That's the question. Okay? The reason why I need to figure out x is because when I have the sine of something plus something, what does this expand out into?
This is, what's it called? Sine A cos B minus plus I guess.
So I'm using the sine addition formula. So it'll be sine A cos B plus cos A sine B. So we're going to use that formula to expand. So sine A cos B plus cos A sine B. So in order to find cos B and cos A, I need the adjacent side to both of these triangles, right? So how can I find the adjacent side for both of these triangles that I've drawn here? Yeah, just Pythagorean theorem. You guys know how to do that. So it's x squared plus y squared equals r squared. X is my question mark. And one thing that I need to make sure of is when I'm solving for x and I do the square root of something squared, there's actually two potential answers for this. X squared equals 16 has two answers. One is positive 4 and one is negative 4. So I need to decide whether x in this quadrant, if I'm going to the left of the y-axis, is negative or if it's positive. So if I move to the left, am I going to the negative side of x or the positive side? Negative. So this must be equal to negative 4, right?
But we just label it as 4, right?
No, I'm going to label it as negative 4. If you don't label it as negative 4, you need to make sure you're using the cast rule. So we know that cosine is negative in that quadrant. Okay, and then similarly for this guy, we will solve. Correct me if I'm wrong, is 13 squared 169?
Yep.
Thank you.
Minus 25, so I think 144, which is 12, if I'm not wrong.
Perfect. And because, again, we're in that second quadrant, yeah, we want it to be negative 12. Okay, awesome. So all we need to do now is fill in our information here for sine of A plus B. We said that's going to be equal to sine A cos B plus cos A sine B. So sine A is already given to us, it's 3 over 5. I'm just going to replace it in my expression here as 3 over 5. What is the cos of B?
Cos would be negative 12 over 13.
Awesome. And this ends up being a negative because we are taking the cosine of an angle in the sine quadrant. So thinking about the cast rule here, if I didn't put that negative in for x, I would need to ensure that I consider the cast rule as I'm entering things in here. So we just used adjacent and hypotenuse in this triangle. Now cos A, that's using this triangle over here. This is adjacent and hypotenuse. So the cos of A should be, yeah, negative 4 over 5. And sine B is given to us in the question. It's 5 over 13. All right, so I think we can just multiply here. 5 times 13, 65. Minus 20 over 65. Should give us negative 56 over 65. So that's the exact value of the sine of A plus B. Hey, if I could, I would also reduce this fraction if necessary. Any questions for that one? We're all okay? Okay.